So radiation cannot have any random amount of energy associated with it. Energy is quantized. And what that means is just that energy has to have discrete values. Right? It doesn't exist on a continuum. It can have a certain amount of energy and then certain multiples of that energy. And when energy is transferred to and from a system, that means it has to be transferred in discrete chunks. And those discrete little chunks of energy are known as quanta. And the energy of electromagnetic radiation is always going to be given by the expression energy equals a constant times the frequency. So in this expression, the E, the energy, is the energy of a single quantum of radiation that has that frequency nu. So let's consider some visible light, some blue light. So we can work out the energy associated with a single quantum of blue light with that frequency. And we can see that the seconds will cancel and we'll be left with an energy in joules. And so we can see that a single quantum of blue light has an energy that is in the range of 10 to the minus 19 joules. And this is a characteristic size. This is a characteristic energy for visible light. Most of the time, visible light is going to have an energy in the 10 to the minus 19 joules range. So if you ever do a calculation and find a number that's wildly different from that, maybe you want to recheck your numbers. And again, we can only transfer energy in discrete chunks, right? So that means that we can't transfer slightly more or slightly less energy than this. So if we wanted to look at 2 quanta of blue light, that would be double the value. And if we wanted to look at 3 quanta or 4 quanta and so on, we'd triple it, quadruple it, and so on and so forth. So for any given color of light, any given frequency of light, you can write an expression for energy. In practice, what this means is there's no blue light source with the frequency of 6.977 times 10 to the 14. There's no blue light source with that frequency that can transfer an amount of energy in between these two values. And each discrete chunk of energy, each quantum of energy, has a special name, and they're called photons. So we can update our energy expression, and we can say that the energy of a photon equals Planck's constant times the frequency of that photon. And we can actually combine that expression with one of the expressions we've seen earlier. So we can connect the energy expression with the speed of light, wavelength, frequency expression. Effectively, all you do is solve each expression for frequency, for nu, and then substitute them into one another. And you end up with an expression that connects wavelength and energy. And generally, we just kind of acknowledge that the energy and the wavelength and the frequency, whatever, are all applying to photons, and we just leave out the subscript photon. And we write E equals hc over lambda. And this means that if we wanted, we could work out the energy associated with any wavelength of light. Or we could work out a wavelength if we had the energy.